Let's do a couple more examples of finding the tangent line. So this time the function we're working with looks like 1 over x, and we're trying to calculate the equation of the tangent line for the x value 2. Remember that the x value tells us what a should be. So if we decide to use the x approaches a notation, we know that a would be 2. We also remember that we need to use that point slope equation, which means we need to find the slope and we need to find a point. The point is probably going to be the easiest part of this problem. The point just comes from taking that a value and then plugging it into our function to find the y value. So if I plug 2 into my function, f at 2, where my function is 1 over x, that becomes 1 over 2. So the point that we'll use, 2 comma f at 2, is just 2 comma 1/2. In other words, our point slope form, we could already plug in our y values to say y minus y1, which is 1/2, equals our slope m, we still have to find that, times x minus 2. Now we just have to find the slope. And that slope calculation comes from our limit. You can use whichever limit notation you'd like. For this problem, I'm going to use the x approaches a notation. So in my numerator, I will have f at x minus f at a, and in the denominator, I'll have x minus a. We can go through and replace all of our a's with 2, since we know that for this problem, a has to be 2, since we're looking for the tangent line at x equals 2. And then next, we should replace our function notation with the actual function definition. So f of x would just be 1 over x, and f at 2 would be 1 over 2. Now, the calculus part of this is pretty straightforward. It's actually quite simple. What makes these types of problems hard is algebra. Tiny algebra mistakes really are the killers of calculus. So have your calculator handy so that you can check your work and make sure that you're not making mistakes because your brain's tired. And open up Geogebra. Plot a graph. See if it looks visually like it's the right thing. We have a complex fraction here. And if I were to plug 2 in directly, I would get a really sad story, actually, because I would get like infinity in the numerator, and then I would get 0 on the bottom, and we don't know how to deal with that yet. So it's a little bit too crazy. What we need to do is simplify this complex fraction. To simplify a complex fraction, we're going to find the LCD. I have a denominator of x and 2, so my LCD is 2. I'll multiply the entire numerator and entire denominator by 2. When I multiply 2x is our LCD. When I multiply 2x times 1 over x, I get 2x over x, which simplifies to be just 2. And then when I multiply 2x times the negative 1/2, the 2's divide off, leaving behind just a minus x. In the denominator, I can multiply the 2x times the x minus 2, but I'm not going to do that. I'm going to leave it factored because every step we make in mathematics, we should do it intentionally. Rather than just applying everything we know as soon as we can, let's take a look at each step of the way and decide if it's smart to multiply it out or if it's not. Taking a look at our new fraction, which is not complex, if I try to plug 2 in, I still get an indeterminate form. But at least this one is a form that we know how to work with. 0 over 0, we've got a few tools that we can use here. One of them is looking to see if we can factor off one of the problems. Now our numerator, 2 minus x, looks pretty close to our denominator's factor, x minus 2, but the signs are reversed. So we can fix that by multiplying by a double negative and taking one of those negatives and sending it into the parentheses. So I would have then a -2 but a positive x. But I would have one extra factor of a negative outside since we had to do a double negative. And then on bottom, my x minus 2 times 2x is still there. Carry down my limit symbol. Technically, we have to keep that limit symbol with us until we actually apply the limit. So make sure you don't forget to write that out. The x minus 2's divide off, leaving behind -1 in the numerator and 2x in the denominator. Now we try again to use direct substitution, plugging 2 in for x, and we see that we get -1 on top and 2 times 2 on bottom for a slope of -1/4. That's the last piece we needed to finish the equation for our line. We can replace the m, which is the placeholder for slope, with -1/4, and then we can clean this up. So we can distribute our -1/4 into the parentheses here, so that we'll have y minus 1/2 equals -1/4 x plus, don't forget I have a negative out here and a negative here. That would make a plus 2/4, which simplifies to be 1/2. Our last step is to add 1/2 to both sides so that we have y equals -1/4 times x plus 1. So that, we think, is the equation of our tangent line. We're going to pop on over to Geogebra and make sure that that's true. We are back at our Geogebra calculator, and we're going to check to make sure that the equation of the tangent line that we just calculated is correct. So we'll start by typing in our function f of x is equal to 1/x. And then remember that we calculated all of this for the value x equals 2. So we're going to plot the point 2, comma, f at 2. Oh, weird typo. 2, f at 2. We see our point on the line, and we can confirm that we calculated that point correctly. 2 and 1/2, perfect. And now we can type in the equation for the tangent line that we found, which was y equals a -1/4 times x plus 1. Notice that this line is the correct tangent line because it passes through the point A and it nicely hugs up against our curve. So, well done, we did it right. Let's do one more. For this function, we're looking at the square root of x, and we want to calculate the tangent line that passes through x equals 4. So we know that a is equal to 4, and we also know that we're going to use the y minus y1 is equal to m times x minus x1. We need to calculate the slope and the point. We know that the point is going to come from plugging a into our function. So our x1, y1 point is the same thing as a, comma, f at a. Our a value is 4, and our function is square root of x. So we're looking at square root of 4 for the y value. In other words, 4, comma, 2. So x1 is 4, y1 is 2. I'm going to go ahead and plug those in right now. Then the only thing left to do is calculate the slope of the tangent line. So let's do our limit. We'll have x approaching 2. On the top, we should have our function minus our function evaluated at the value 2, and then in the denominator, x minus 2. If we try to use direct substitution right here, we will find indeterminate form, but we have a trick to help us with radicals where there's a sum or a difference between the terms. So what we'll do is multiply by the conjugate. So let's do a little bit of scratch work down here. I'll copy down the expression that we have inside of our limit. Uh-oh, I changed my a to 2. I was thinking about the last problem we were doing. Let's fix that. That should be 4. That should be 4. That should be 4. So then we have 2 up here. There, tiny mistake. Caught it before it was a big deal. Lucky us. All right, I want to multiply by the conjugate. It's the numerator that has the radical, so I will conjugate the numerator, and I'm going to multiply that to both the top and bottom. I'll pop parentheses around everything to make sure we know that we need to FOIL this. Or we can use that difference of squares pattern. I have root x minus 2 and root x plus 2, so that would look like root x squared minus 2 squared. And in the denominator, I'll leave that factored because I'm really hoping that the problem is going to divide off once we simplify our numerator. If I square a square root, that leaves out x, and technically it would be the absolute value of x. But good news for us, our limit is having x approach a positive 4. So since we're staying in the positive range for x, we don't need those absolute value bars. So we have x minus 4 on top, and then we have the product x minus 4 times root x plus 2 on bottom. The x minus 4 factors divide off, leaving us with 1 over root x plus 2. So this indeterminate limit, we can rewrite that using this little twin function we found, which is 1 over root x plus 2. That function will work with direct substitution. I plug 4 into the x, and I get 1 over root 4 plus 2, which is just 1 over 2 plus 2, or positive 1 over 4. And let's jump back over to Geogebra and see that, well, wait a minute. We need to plug that into our slope. I'm getting ahead of myself. So we need to replace our m with a positive 1/4. And I'd like to clean this up before typing it into Geogebra as well. Let's do distribute the 1/4 into the parentheses. So, and I'll write that down here. We have y minus 2 equals 1/4 x minus 1/4 times 4, which would be 1. Then I'll add 2 to both sides so that I get y equals 1/4 times x plus 1. That's our tangent line. This is what we want to plug into Geogebra to make sure that it is tangent to the function root x at the value x equals 4. We're back at Geogebra. We'll type in our function f of x equals square root x. Geogebra's being difficult. There we go. Square root x. So we have that graphed. Then we want to graph the point 4, comma f at 4. We have the point, and now we're going to graph our tangent line. Y equals 1/4 times x. Be careful that you don't type x down into the denominator. That will change everything. It's 1/4 times x, and then plus 1. And we can see that we've definitely done this problem right as well. We're passing right through that point A, and our equation of the tangent line is nicely touching the function right at that point.